Welcome back, chemistry students. This next bit is all about precision and accuracy. A measurement is said to be precise if it yields very similar results when repeated in the same manner. So if you get the same or very similar measurements over and over and over, then your measurements are precise. A measurement is considered accurate if it yields a result that is very close to the true or the accepted value, which is something that you would need to be told. Here's an example where we have a bullseye. We know that the bullseye is the very center of the target, and that's what you aim to hit, right? So that would be our accuracy point. Here we've got 3 darts that have been thrown in there, boom, 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 all right there. So these arrows are not only just close to each other, but they are right at the bullseye. So they're both accurate and precise. For B, we've got boom, 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 3 thrown right in a row, but we're not at the bullseye. So while they're close to each other, they are precise, but they're not accurate. And then over here for C, we have 3 darts kind of not too close to each other. If I was showing this as an example, I probably would have had 1 dart here, 1 dart here, 1 dart there. That would be not precise and not accurate, but that's just me. Here I have 3 different dispensers of cough syrup. Each dispenser is 296 milliliters. So we're trying to see which dispensers are either precise or accurate or both or neither. Let's look at dispenser 1. We're at 283.3, 284, 283.9, 284.0, 284.1. Those measurements are all really close to one another. These two are only a tenth apart. This one's a tenth apart. These two are a tenth apart. So pretty darn close to one another. I would say that they are precise, but is it accurate? Is it 296 or very close to that? No. I'd say that they're precise, but not accurate. Why don't you decide what dispenser 2 and dispenser 3 would be? Did you decide that dispenser 2 is more accurate but less precise? Notice that I've got a range of 298 all the way down to 293. That's a pretty big range. That's almost a 5 milliliter range. So less precise, but more accurate. We're right around that 296. What about dispenser 3? I would say that dispenser 3 is both accurate and precise. We're only a tenth away from the targeted value here and there and there. We're spot on there and then a tenth off there. How would you label these? For this first one, I would say, those measurements are not quite close to each other, but they are pretty close to the bullseye. Not at the bullseye, but I would say not precise and somewhat accurate. It doesn't have to be an all or nothing. Over here for this guy, we've got pretty precise measurement, but definitely not accurate. For Y, we have not precise, not accurate. And I would say the same thing for Z. Not precise, not accurate. All right, we are getting into some numbers in chemistry. We are going to look at scientific notation and significant figures. Scientific notation is a way to express very large or very small numbers. It helps to avoid confusion. Scientific notation is always set up in this format where I have a number that is between 1 and 9.99 times 10 raised to the nth power. If n is less than 0, meaning is it a -1, a -2, so a negative number, then it is a very small number, meaning it's less than 1. It's a decimal. If n is greater than 0, then it is a very big number, so in the tens, hundreds, thousands, millions, billions, trillions. So let's look at this. We've got a very large number here. This is how many helium atoms are in 1 liter of helium gas. Let's express this number in scientific notation. I like to take my pencil and put a dot to make it a number between 1 and 9.99. So if I were to put a dot right here between the 2 and the 6, that would make it 2.68. And then you say times 10 raised to the, now we got to figure out how many spots do I have to move my decimal point to get back to where it originated, which would be right here. So that would be 3, 6, 9, 12, 15, 18, 21, 22 spots. 2.68 times 10 to the 22, and we always want to label atoms. of helium. And notice that this N, this number, is greater than 0, making it a very big number, which it is. Here's an example of a very small number. Notice that it's a decimal. It's 0.000, I don't know how many zeros, 116 meters. So it's a small number. That means that my number is going to be times 10 raised to the negative something. Let's figure that out. Again, I'm going to take my pencil and I'm going to put a decimal point in between the numbers to make it between 1 and 9.99. So that would be 1.16. And then I'm going to say how many spots backwards do I need to go to get back to where it originated? And I need to go back 1, 2, 3, 4, 5, 6, 7. So 1.16 times 10 to the negative 7th, and it was in meters. Pause the video here and express these ordinary numbers or regular numbers in scientific notation. Did you get 1 times 10 to the 5th? 1 times 10 to the negative 8, 1 times 10 to the 7th, 1 times 10 to the negative 12, and 6.65 times 10 to the negative 24th grams? Let's go the other way around and take the scientific notation and put it in an ordinary number. Pause the video here to check your answers. If you were to be doing some calculations, your calculator might spit out an answer that looks like this, the 7.45 e negative 17. E means times 10 raised to the, and then negative 17, obviously, is to the negative 17th power. But that e means times 10 raised to the, or caret, number. All right, let's get into significant figures. Numbers that are always significant are non-zero digits, meaning 1, 2, 3, 4, 5, 6, 7, 8, 9. Captive zeros are always significant. So 101, that 0 is a captive 0, or sometimes I like to say it's a sandwiched 0. Trailing zeros, but notice that this says trailing zeros are always significant and this says trailing zeros are not significant. So sometimes they are and sometimes they aren't. They are important when they are to the right of a decimal and to the right of a number. So 0.10. This 0 is to the right of the decimal and to the right of the number. But if I said 0.010, while this 0 is to the right of a decimal, it is not to the right of a number, if that was a 0 right here. So that 0 is not significant, but obviously 1 is, and that 0 is significant. This would have two significant figures. Zeros are important when they are written in scientific notation, as in a trailing 0. So if I said 1.00 times 10 to the third, those zeros are always important in scientific notation. Everything that is written in scientific notation is significant. Numbers that are not are leading zeros, meaning if I said 0.0004, all right, the 4 is significant, but all of the zeros before it are just leading zeros. Now, if I had a 1 right here, if it was 10.00004, now all of a sudden all of these zeros are sandwiched zeros and they are significant because of that 1 being there. But if there was no 1, all of those zeros are just leading, non-significant, and the 4 is the only significant digit. Trailing zeros that are not significant are when they are to the left of the decimal place. So if I said 100, these zeros are trailing zeros to this 1. This 1 is significant. Obviously, it's a non-zero number. But these two zeros, they are trailing and they are to the left of the decimal spot. If there was a decimal spot, it would be right here. We're not going to put it there because then that makes those zeros significant. But if I said 5,280, obviously the 5 is significant, 2 is significant, 8 is significant, but not that 0. That is a trailing 0 to the left of the decimal spot. If I looked at this number right here, the 3090, the 3 is significant, the 9 is significant, the 0 in the middle is captive, so it is also significant, but that 0 is trailing, not significant. This number right here, I have leading zeros, not significant. Obviously the 8 and the 2 are. That 0 is sandwiched, it is. And this 0 is a trailing 0 to the right of a number and the right of a decimal. It is significant. This would have 4 significant figures. When you are in the lab and you are taking measurements, All numbers from measurements are significant. However, oftentimes when we start doing calculations, we get a lot of numbers that our calculator spits out. So we get a lot of non-significant digits. We then have to round off. So there's some rules for rounding. If the first non-significant digit is less than 5, you just drop all of the rest of the digits. If the first non-significant digit is greater than 5, then I need to increase the number by 1 that's right before it. For example, if I said 1432.7, and I said, oh, I can only have 4 significant figures, 1, 2, 3, 4. You go, all right, well, this is the first non-significant digit. Will that 7 do anything to the 2? Yes, it rounds it up, 1433. So that's all that's saying. It's just like math rounding. If a calculation has several multiplication or division operations, don't do any rounding until the very end. Let's do some practice with rounding. Let's say you do some calculations and you get this big number, 15 point blah, 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 and you only can have 3 significant figures. So you're going to go 1, 2, 3. After that 7, there's a 3. That 3 is not going to do anything to that 7, so 15.7 would be your answer. If this is what your calculator spits out and you can only have 3 significant figures, you would go, all right, the 1, the 8, the 7, and that 5 will round that 7 up to an 8. So 18.8 would be your answer. Let's say that I have to round to 2 significant figures and I have a number like 183. So I would say, okay, 1 is the first sig fig, 8 is the second. That 3 is not going to do anything to that 8. So it's easy to just say 18. But hold up, 183 is not anywhere near 18. So when you have to do that, you just put a 0 in as a placeholder because we know that trailing zeros are non-significant. So we would have 180 milliliters right here, not the 183. Let's look at this guy and round it to 2 significant figures. I'm going to go 1, 2. That 4 isn't going to do anything to that 8. So just 48,000 grams. Why don't you try rounding all of these numbers to 3 significant figures? Check your answers. So for review, if a number is less than 1, so 0.001, that's a number that's less than 1. All of those placeholder zeros are never significant. So these 3 numbers all have 1 significant figure. If a number is greater than 1, a placeholder 0 is usually also not significant. So 50, 500, and 5,000 all also have 1 significant figure. Write down how many significant figures each of these measurements have. Pause the video here and check your answers. The first one are all non-zero numbers, so they are all significant. Letter B, this is a leading 0, so not significant, just those 3. This is another leading 0, not significant, just 1. This is 4 significant figures because this 0 is sandwiched, and the second 0 is after the decimal spot and after a number. 2005, the 2 zeros are sandwiched. They are important, so 4 total. For F, those zeros are after the decimal and after a number, so 5 sig figs. 3 sig figs for G, and just 2. This is a leading 0, not significant. Pause the video here to try these ones. Check your answers. Pause the video here and round these to 3 significant figures. Pause the video again and check your answers. Sometimes we have to add and subtract measurements. When you add or subtract different numbers, your answer is limited by the value with the most uncertainty. In this case, I've got 3 numbers. This number is to the 10th, this number is to the 100th, and that one's to the thousandths. This guy is the most uncertain number, the tenths. They all have the tenths in common, so therefore, when I add them all together, I'm going to plug them all into my calculator, add, and you get this number that your calculator spits out, but you have to round your answer to the tenths because this is what you're limited to. So if you're adding or subtracting, that's the rule. Try adding and subtracting these 4 numbers and round to the correct number of significant figures. Check your answers. When you're multiplying or dividing measurements, your answer is limited by the value with the fewest significant figures. So if I look at multiplying these 2 numbers, I count and say, okay, he has 3 significant figures and he has 2 significant figures. So the smaller 3 versus 2, 2 wins out. So when I get an answer that my calculator spits out, I need to round that to 2 significant figures. That would round to 33 centimeters squared. Knowing the rules for multiplying and dividing, try answering these 4. Check your answers. You have to be aware about what your calculator says. If I added these 2 numbers together and used my calculator, it would spit out the number 6. However, that's not correct. We need to be significant to the one that has the most uncertainty. In that case, that's to the hundredths. So I would need to report it as 6.00. So be aware of that. Your calculator might not always be right. In this case, if I typed in 36 times 73, you're going to get this big number on your calculator, and you need to go, oh, 2 sig figs times 2 sig figs. I need to finish with 2 sig figs. 2600, because that 2 is not going to do anything to that 6. This is our last piece of information. We are looking at the percent concept. The percent is expressed as the amount of a single quantity compared to an entire sample. So part divided by whole. A percent is a ratio of parts per 100 parts. So 25% can be expressed as 25 over 100, just as easily as if I ate 1 piece of pizza and there was only 4 pieces of pizza. If you typed into your calculator 1 divided by 4, it would tell you 0.25, and then we times it by 100, so 25%. So it doesn't always have to be just 25 over 100, but we can reduce that 25 over 100 to get 1 over 4. 10% can be written as 10 over 100, which we know can reduce to 1 over 10. We can use a percent expressed as a ratio as a unit factor. So if I have my quantity or my part over the total sample times it by 100, that tells me the percentage. Here I have the Earth and Moon having a similar composition. They have 4.70% iron. What is the mass of iron in a lunar sample that weighs 92 grams? So it's asking me to find the part, we'll call that X, over the whole 92 grams. And when I do that and times it by 100, it's 4.70%. We need to find X. So let's just work backwards. I'm going to get rid of this 100. Since I'm timesing it by 100 here, I'm going to divide both sides by 100. That gets me X over 92 is equal to the 0.0470. And then I'm going to cross multiply because I don't like solving fractions, so I'm going to make it linear. Cross multiply these is equal to X. And then I'm going to multiply 92 times 0.0470 to get 4.324 grams of iron. And then actually I need to be more specific. I have 3 significant figures in that percentage, 2 significant figures in that mass. I should finish with 2. 1, 2. That 2 is not going to do anything. So 4.3 grams of iron. Pause the video here to solve this example. Did you get 88%? All right, that wraps up chapter 1.